नमस्ते। आप सभी का इस लैब सेशन में स्वागत है। आई एम प्रोफेसर सुबोध वी मोडक. So in this lab session we are going to solve some problems on control system analysis using MATLAB and Simulink. So let me show you the problem sheet we are going to have, like this one. So there are several exercises. The first few of them are based on MATLAB, and then we have some exercises based on Simulink. So in the first exercise, we have to essentially define a transfer function. That's the first task, right? So I have already developed a MATLAB code for this, and you can see this is the MATLAB file. Okay, so this clear all generally is used to ensure that we clear all the variables in the workspace. CLC is a command to clear the screen. Okay, the command window, it can be cleared using this. Uh, Now, to define the transfer function, which is given as, let us look at that, that is 1 upon s square plus 5s plus 6. So this transfer function consists of ratio of numerator polynomial and denominator polynomial. So in the MATLAB, therefore, we first define the numerator polynomial. So num is a variable we have chosen, and it is just 1 in the numerator. And then in the denominator, we have the polynomial, uh, whose coefficients are 1, 5, and 4. So 1 is the coefficient of the highest order term in the polynomial, and uh, then the second highest, and then the last highest, right? So in this way we define this polynomial. Then we use the command transfer function. TF is the MATLAB command to define the transfer function. And the numerator and denominator polynomial coefficients are the input to this command. And systf is the user defined name of the transfer function, user chosen name of the transfer function. Here I have chosen systf. uh, so if you now run this program, then you can see now in the command window we can see the output. So num is the vector of the numerator polynomial coefficients, then dn then is the vector of the denominator polynomial coefficients, and then it defines systf as a transfer function, which is 1 upon s square plus 5s plus 4. So the next task in this exercise is to convert this transfer function to pole zero form. Okay, so the pole zero form means we have to express the transfer function as the ratio of the factors in the numerator and the denominator, and those factors are based on the poles and zeros. uh, so you can see here in this file, the command which is used is tf2 to zp. Tf means transfer function to zero pole form. That's why it's easy to remember this command, tf to zp. And again, the numerator and denominator polynomial coefficients are the input to this command, and the output is zpk, right? So zpk means z is the vector of zeros, which is the roots of the numerator polynomial. P is the vector of poles, which is the roots of the denominator polynomial, and k is any gain constant in the numerator. So let us execute this. So we simply enter it. So you can see here, this is the output. So here, the because the numerator polynomial is a constant, right? So therefore there is no zero. So there is no finite zero. So zero is, z vector is empty, right? There is no zero. Now the p vector, it shows that there are two poles, -4 and -1, right? So obviously these are the roots of the denominator polynomial of the transfer function. And then there is a constant 1 in the numerator. So in this way, we can convert the transfer function from uh, which is the ratio of the two polynomials in S. We can convert it to a form which is defined in terms of the poles, zeros, and the gain of the transfer function. The next task in the exercise is to convert the transfer function to the partial fraction form. So in this, essentially, we break down the transfer function as sum of different partial fractions, right? So the the command which is there in the MATLAB to do that is residue. Okay, so and again the numerator and denominator polynomial coefficients vectors are the inputs, and then the output is rpk. So no, the p essentially are the poles, right, or which are essentially the poles of the different terms in the partial fraction expansion, right? So they are the roots of the different terms in the partial fraction expansion, and r is the vector of residues, which is essentially the uh, the numerical coefficients in the numerator of the different terms in the partial fraction. K is any term, any constant term which is added to this partial fraction expansion. So if there is a constant term, then this K would be non-zero. So let us run this and see what is the output. So you can see in the command window, we see the output. So here the residues, you can see there are two terms in the partial fraction, and the residues, the numerical coefficients in this of these two terms in the numerator are minus 0.33 and 0.33, and the poles of the denominator of these partial fractions are minus 4 and minus 1. So there are two terms in the partial fraction, right? And K is empty, which means that there is no constant which is to be added to this expansion, right? For this particular transfer function we have analyzed. Now the last task in this exercise, the task D, is to convert the transfer function to state space form. So the command for this is very simple. It is tf2 to ss, which means the convert the transfer function from tf form to ss form, that is the state space form. And the numerator and denominator polynomial coefficient vectors are again inputs here to that command, and output is in terms of the matrices A, B, C, D, right? Which are the matrices in the state space model of the this transfer function. So let us run this. So the output we can see in the command window, the four matrices. Okay, so you can see A is the A matrix, state matrix, which is of size here 2 by 2. The reason is that the transfer function we have got is this gs is equal to 1 upon s square plus 5s plus 6. So it represents essentially a single input, single output system. And then the transfer function is of second order. So if it's a second order system, then there are two state variables that are required to describe the state of the system at any instant of time. And that is why the state matrix is of size 2 by 2, as we see in the output. Okay. Now the B matrix, which is the input matrix, is here of size 2 by 1. That is because there is one input. It's a single input, single output system. There is only one transfer function. So there is one input, and then there are two states. So that is why B matrix is of size 2 by 1. Then the output matrix C is of size 1 by 2. That is because it's a CISO system, so there is only one output. So one output and two states. Therefore, the order of this output matrix is 1 by 2. And then D matrix, which is direct transmission matrix, also called as feed through matrix, is 0, right? Because here the output, there is no effect of the the input directly affecting the output of interest. And that is why D is 0 here. So in this way we see the state space model. In this therefore exercise we use we define the transfer functions by defining the vectors which contain the coefficients in the numerator and denominator polynomial. There is another way to define the transfer function. You can see here the alternative method is this. So here to the tf command, if we pass this variable s in this form, inverted comma, then this s, then it creates a variable s. On the left hand side there is s, so it creates a variable s. Okay, and using this variable s we can simply define the transfer function, right? By directly typing or by directly keying in the formula for the transfer function. You can see here. So after the this particular command, what happens is that the s is defined as a variable, and then we simply you know define our transfer function as 1 upon s square plus 5s plus 6, right? So let us run this. So you can see here, so in the command window, the transfer function is defined, which I have called as systf1, and that is exactly same as what we wanted, correct? So this is another convenient method to define the transfer function, right? So if one doesn't want to define the polynomial coefficients, then one can use this method to define the transfer function. So in this way we come to the end of the first exercise, okay? And let us go to next exercise, exercise 2. So in this exercise, for the closed loop systems shown in the figure, we have to use the MATLAB commands and find a closed loop transfer function. So in this exercise, we are going to learn some commands by which we can define the transfer function and then combine those transfer functions in order to find the transfer functions of the closed loop system, okay? So in the part A, you can see this is the block diagram. So therefore what we are going to do is define this transfer function 10 upon s into s plus 1, and then find the transfer function of this feedback loop. So let us go to the exercise 2. This is exercise 2, you can see here. So we first define the transfer function 10 upon s into s plus 1. So numerator polynomial coefficients are defined 10. And now in the denominator there are two terms, s and s plus 1. So s plus 1 can be written as can be defined by this vector den 1, 1 1, which are the polynomial coefficients of s plus 1. And then for s, the polynomial coefficients are 1 and 0. 1 is the coefficient of s and 0 is the constant, right? And then now we multiply these two polynomials, s plus 1 and s, and for that we use the command conv, convolve. So we convolve these two polynomials together, den 1 and den 2, and that gives us the polynomial den, right, which is the complete polynomial in the denominator. And then we pass on these numerator and denominator polynomial coefficient vectors to the tf command, which then defines the transfer function g. Now after this, now we define the transfer function in the feedback path. The feedback path, you can see here, there is a direct transmission of the signal C to the summation junction. So there is unity feedback, okay? The transfer function of this feedback path is unity. So therefore if we say h is the transfer function of the feedback path, then h is 1, right? So you can see, let us run this much part of the program. So you can see here in the command window, we have got this g transfer function, which is 10 upon s square plus s, right, which is same as 10 upon s into s plus 1. So this is the transfer function in the feed forward path, right? And h is equal to 1 is the transfer function in the feedback path. And now there is a command in MATLAB, feedback, okay? So this feedback command requires two inputs. One is the transfer function in the feedback in the feed forward path, which is g here, and the transfer function in the feedback path, which is h. So when that is given, we get the transfer function of the feedback loop, which I have called this as GCLA, right? That is the closed loop transfer function for part A. So let us run this. So let me just simply enter here so that I go forward the pause, and you can see here it has now found out the transfer function of the closed loop system, 10 upon s square plus s plus 10. You can easily verify this using the the thumb rule which we have studied earlier. That is the closed loop system transfer function, C by R is equal to feed forward transfer function upon 1 plus open loop transfer function, okay? So, and you would see that this exactly matches with what we got here through MATLAB command, right? Let us look at the next part of this problem, the closed loop system given in part B. Now this closed loop system has got two loops. One is the inner loop, and then there is an outer loop, right? So now what steps we are going to follow? First of all, we will find the closed loop transfer function for this inner loop by following the steps which we followed for the part A. Then we will combine the closed loop transfer function for this inner loop to the transfer function of this block, which is 1 by s, integrator block, right? That would give us the transfer function of in the feed forward path. And then we will use one feedback command once more in order to essentially find the closed loop system transfer function of this outer loop. Okay, so let us go to the program. You can see here this is part B, and in part B you can see I have defined the transfer function G1, right, which is the transfer function in the feed forward path of the inner loop, right, which is you can see here it is 10 upon s plus 1, that's all. So you can see the 10, this is the numerator polynomial vector 10, 1 1 is the denominator polynomial vector, and then using TF we get G1, right. Now we define the gain kh, which is given as 4, right, and then h1 is the transfer function of the feedback path of the inner loop. So h1 is nothing but kh, right. We can see from the this thing, you can see kh is the transfer function of the feedback path. And now we use the feedback command to combine the feed forward transfer function G1 with the feedback path transfer function H1, right? And that gives us the transfer function of the inner loop, G inner loop, right? So after that, then we define the transfer function of the feed forward path of the outer loop, right? Of course, first we are going to define the transfer function of the block 1 by s. So this G2 is the transfer function of block 1 by s. 1 means the numerator is 1 and the denominator is s. So the polynomial coefficients are 1 and 0. Okay. And then therefore now we combine G inner loop with G2. They are in series. So there is another command in MATLAB, series, which allows us to combine two blocks in series, right? That is in cascade. So G inner loop and G2. So when we combine them, we get GFF, which is the transfer function of the feed forward path. So also, whenever you use different variable names, it's good strategy to use the names which make which are related to the variables, right? Instead of using some arbitrary names. So G is the transfer function, FF is the forward path transfer function. So the very useful name could be GFF. Now after this, we define the feedback path transfer function of the outer loop, which is 1, okay, which is unity feedback, and then we combine these transfer functions GFF and H2 using the feedback command, okay, which gives us the transfer function of the outer loop, which is GCLB, closed loop transfer function for part B. Okay, let us run this. So let me just enter here, and you can see it has given us the output. So you can see here, first of all, we get the G2, you can see G2 transfer function, which is 1 by s. Then we get GFF, which is the feed forward transfer function of the outer loop, which is 10 upon s square plus 41s. And then we have H2, which is the feedback transfer function of the outer loop, which is 1, and then the closed loop transfer function of the whole system, which is GCLB, correct? So in this way, we see that how we can make use of the feedback series commands. There is another command parallel by which you can combine the two blocks in parallel. Therefore, the transfer function will be sum of the individual transfer functions. Of course, that we are not used in this particular exercise. That was not required. Okay. So let us go to the next exercise now. So the next exercise is about exercise 3, that is by writing a MATLAB program, find the unit step and impulse responses of the following systems for 12 seconds, taking a time step of 0.01 second, and then plot the responses. Okay. So let us open exercise 3, which already I have done. You can see here. So this close all, this command, whenever it essentially closes all the figures which are currently open. Okay. So the advantage is that whenever I run this program afresh, all the existing figures will be closed down, and then any new figures in the program would be generated. So let us, you can see there are two transfer functions given to us, g of s 100 upon 2s plus 1. In part B we have 10 upon s square plus s plus 25. So I'm going to show you how to obtain this impulse and step responses for part B. For part 1 you can easily then apply the same steps. So therefore again the first step is define the transfer function, as we have done in the first two exercises. You can see numerator and denominator polynomial coefficients. So, and then we define the transfer function sys and now we define a time vector, because for 12 seconds we have to simulate the system with a time step of 0.01 seconds. So in the MATLAB very easily this vector can be defined. So 0 is the starting time, and then there is a colon, and then we have 0.01 which is the time increment, then colon, and then 12 which is the the ending time, the termination time 12. So this is going to generate a time vector of 12 seconds with an increment of 0.01 seconds. And now we define figure. So when we say announce figure, so it is going to essentially make a new figure, and whatever plot is made, it will be inside that figure. And then there is a MATLAB command step. This command requires at least the system transfer function which we have given here, and then providing time vector is optional. If we don't give any time vector, then the MATLAB command would choose its own time vector. Okay, and then if time vector is given, then obviously it will find the response for the time vector that is given. The grid essentially draws a grid in the xy plane. So and then similarly we can find impulse response, unit impulse response, using the command impulse. And here again we have to give the system transfer function and the time vector, which of course can be skipped if we want to use the default time of the MATLAB. Okay, let us run this now program. So it's busy, it's taking some time to calculate the response, and now it has plotted. Let us look at the first plot. So this is, you can see the step response. On the y-axis is the amplitude, on the x-axis is the time. So this is the unit step response of the system. You can see the system that is given to us is second order system, and it happens to be an under damped system. Okay, so damping in the system is less than 1. And now we see that the step response, it starts from the origin, right? And then it undergoes oscillation, and gradually the amplitude of the oscillation, they decay, and then it reaches to some steady state, and the steady state value of the response is 0.4. Okay, so this is the unit step response of the system. Let us look at the impulse response. This is the impulse response. The impulse response is response of the system to a unit impulse. So it starts from 0, okay, and then it undergoes cycles, oscillations, the amplitude of oscillation, it decays, and then finally the response becomes 0. Okay, so unit impulse response would become 0 as t tends to infinity. So this is how you can find a unit step response and unit impulse response of the system. Let us go to the next exercise. In the exercise 4, now here the exercise is to find response of the system in 3b, right? Means the transfer function is given to an input which is a half sine pulse of 5 seconds long duration, having an amplitude of 8 units, and then find the response for 15 seconds, taking a time step of 0.01 seconds, and then plot both the input and output response. So here the input is more complicated. It is not a standard input like a unit step input or an impulse input. Here there is 5 seconds of pulse, which is half sine pulse, right? And then after that 10 seconds there is no input being applied. Okay, so let us look at how we can find a response to such an input. So let me this is in the exercise 4. Okay, so again here we define the transfer function as we did previously. You can see here we are defining the transfer function, and now we are going to define now the time vector and input vector. So you can see here the first for 5 seconds the pulse is there, so let us call say pulse time is a variable. Let us call it phi, assign the value phi, and now the sine wave whose part this pulse is, the frequency of that sine wave would be 1 upon the time period of the sine wave, And what is the time period of the sine wave? It is twice the pulse time, because pulse time is the half sine pulse. So double of that would be the time period of the sine pulse. And then the inverse of that is the frequency in hertz, right? So that is the frequency. Uh, Next, we define a time vector from 0 to 5 seconds. Okay, so you can see here 0 to 5 seconds with an increment of 0.01. Now we define the input vector, the pulse vector. That is essentially a half sine wave. So amplitude of the sine wave is 8, and then it's a sine wave, so sine 2 pi. Frequency is frequency in hertz into time vector. So you can see this is a nice thing in MATLAB, that the vectors and matrix operations can be performed simply in one line, right? You don't have to write make for loops for performing vectors and matrix operations. So here you can see t vec pulse is a vector, and now we can pass this vector to the sine function, and then it will take the sign of each of those elements in the vector. Okay, so in this way pulse vec is a sine vector uh, you know corresponding to the half pulse of the sine wave. Now, but then we would like to define the time vector for the whole time of 15 seconds, right? So we define total time as 15, and then we define time vector for the whole total time with an increment of 0.01. And now we define the input vector for this 15 seconds. So we initialize the input vector with zeros of the same size as that of the complete time vector. And now we replace the first 5 seconds of this input vector by the pulse vector. So you can see u vec, the 1 to length of t vec pulse, that is the 5 seconds, from means up to the time vector up to 5 seconds. That part of the 2 vec we are replacing by the pulse vector. So you can see in MATLAB very easily and nicely we can perform the matrix manipulation, vector manipulation, and that reduces the length of the program, and and also the time of execution becomes faster, right? Uh, and now what is the command to find the output response? So output response, the command is LSIM, which essentially is abbreviation of linear system simulation, right? LSIM. And the input to this command is the system transfer function, which is systf, input vector, which is uvec, which already we have defined, and the time vector, okay, for which the uvec has been defined, and outvec is the output of this command. So that will essentially give us the output. Okay, and then we would like to plot this. So figure is the we are saying that that is the figure in which we would like to plot the input. So plot is the again MATLAB command. The first the input is the time vector, that is the x-axis. On the y-axis the input is given in the what we want to plot is the input vector uvec. R is the color of the line which will be used to plot this figure. R is for red, right? And then x label allows us to write the label on the x-axis, which is time. On the y-axis we would like to write the label input, and then grid allows us to essentially make a grid, overlay a grid on the figure. Similarly, we would like to draw another figure, so we say figure again, and then plot in this in this figure we would like to plot the output vector, right? And again y label will be the output. So this completes the program. Let us execute this program. So you can see here the first figure is the plot of the input. So you can see for the first 5 seconds it's a half sine pulse, right? And for the remaining time from 5 seconds to 15 seconds there is no input, so that is all zero. So therefore we are finding the response of the system to this kind of input. You can think of this like a speed breaker, a car moving over a speed breaker, right? And then the car being modeled by a second order system, right? And let us see how the car is is going to vibrate in the vertical direction. So let us look at the figure 2. So you can see this is the output, the displacement of the system. So for the first 5 seconds you can see how the system is undergoing the displacement, and then at 5 seconds there is no input acting anymore. So system undergoes a transient response, right? So in the first 5 seconds, you have both transient response, and the steady state response, and then after 5 seconds, there is only transient response which is there, and steadily that response decays. The transient essentially decays, and the system comes to rest position, right? So therefore, in this exercise, we have learned that how we can analyze the system for any general input. So you have to essentially define that input properly, define the time vector, and essentially pass the input vector and the time vector along with the system transfer function to the LCM command in order to obtain the system output. Okay. So this essentially allows us to find response to any general input. Let us go to the next exercise. So mm, exercise 5. Mm, So I think, yeah, in exercise 5, a unity feedback control system has a proportional controller CS to control output of a plant whose transfer function is this, right? Uh, and then through a MATLAB program, find the response of the closed loop system to a need step reference input for controller CS given by K, and where K is 1, 5, 25, 100, right? And then we have to obtain the overlay of the time response plots for this system, and also we have to write our observations. uh, so in this system you can see, in the first 4 exercises we analyzed the open loop system. We in fact, no, the second exercise was about the closed loop system, but then in this exercise we are going to look at, going to study what is the performance of a proportional controller. Okay, the plant transfer function is given, the controller is a proportional controller C of S, and it is defined by gain K, and different gains are given. And so here we are going to study how the gain of the proportional controller affects the closed loop system performance. Correct? So here it is suggested that we use a for loop to make a compact program, because only we have to vary the gain of the controller. So what we would do is that we would make a for loop, and then change the gain, and then plot the the output of the feedback loop, output of the system, to a unit reference input, right? And see that whether the output is able to follow the reference input or not, right? So because the that is the objective of this feedback control system, that the output of the system must track or follow the reference input. So having an overlay will help us to understand and get an insight into what is the effect of gain K on the ability of the system to follow the reference input. Let us look at the program. So this is exercise 5. Okay. So here, we are now going to define the transfer function, plant transfer function. You can see here. Here I am first of all define the plant transfer function G, uh, you know, and next then we define the gain vector, K vec. Okay, the gains are given in the problem 1, 5, 25, and 100. And then we define the time vector. Okay, so T vec is starting time is 0, end time is 12, and increment is 0.01. Then we define, we initiate a figure, and this is done outside the for loop, because in the same figure we would like to plot the output response for different values of the gain. Okay, so all the plots would be overlaid into a single plot. And then since there are 4 gain values, so we start the for loop with jj 1 to 4, and now we will first define the feed forward path transfer function. The feed forward path consists of the plant transfer function and the controller, which is the gain K. And already we have defined the gain of the transfer function of the plant, which is G, and the controller transfer function is simply the gain K. Therefore, we would like to first take the gain as K vec 1, right? So K vec JJ essentially picks the first gain in the gain vector, which is 1. So systf is the feed forward path transfer function, and then the system has unity feedback as given in the problem. You can see here, unity feedback closed loop system. So the feedback path transfer function is unity, right? So that's why h is 1, And now we use the feedback command we studied in the one of the previous exercises to find the closed loop transfer function. So sysdf is the feed forward part transfer function, h is the feedback part transfer function, and we get gcl, which is the closed loop system transfer function for the current value of the gain, right? And now we find the step response, step gcl tvac. So this will essentially plot the step response in the uh, current figure window, right? And now this command hold on is used to plot any further plot which is made on the same figure, right? And returning the any existing figure, any existing plot in that figure, okay? Uh, and then the for loop ends. So in this way, essentially, this program will be able to overlay the step responses, unit step responses of the closed loop system for different values of the gain. Let us run this program. So it's busy, oh, so it has done the job. You can see the units, the step response, for different values of the gain has been obtained. So this the lowest figure here, lowest plot here is for the gain k is equal to 1. This is for gain k is equal to 5. This is for 25, and this is for 100. So what are the observations? The observation is that as the gain is changing, the nature of the system is changing. You can see here, when gain k was 1, we don't see any oscillations, right? But however, with the gain uh, increase to 5, 25, and 100, the system is now showing oscillations. You can see here there is a small oscillation, and then you can see gain k is equal to 100, there are oscillations. It means the nature of the system is changing from being an overdamped system to underdamped when the gain k is changed of the closed loop system, right? That is the first observation. The second observation is that look at the steady state value. When gain k was 1, there is a steady state value here is something like probably around 0.18. And what was the unit step input, reference input? That was 1, right? Units, because we have found the unit step response. So the reference input was 1, but the output is 0.18. So the output is not very close to the reference input. So this controller with gain k is equal to 1 is not performing satisfactorily. With gain k is equal to 5, the output is around something like 0.42, right? Around that value. So now the steady state error has reduced, right? You can see because 0.42 is closer to 1 than 0.18. And with gain k is equal to 100, the steady state value is something like 0.95 approximately, right? And 0.95 is very much close to 1. So it means that now this controller is doing the job of tracking the reference input much better. Because the output of the control the feedback loop is closer to the reference value. Although it is the steady state error is not completely zero, which means that the output is not exactly tracking the reference input. However, it is pretty much close to the reference value, right? So therefore this particular exercise has helped us to understand how the gain of the proportional controller affects its performance, correct? Also, one drawback of increasing the gain is that with lower gain the system didn't have overshoot. Okay, you can see the gain k is equal to 1, there was no overshoot. But with gain k is equal to 100, system is overshooting the desired reference value. Okay, and then so it is oscillating about that final steady state value. So this is the drawback of increasing the proportional gain k. Let us go to next exercise now. Exercise 6. Now, in these last three exercises, we are going to now make use of Simulink in order to model the physical system, any given physical system. So in this exercise, we have to make a Simulink model of a DC motor subjected to an input voltage V and disturbance torque TR. Use the following parameters for the motor. So the inductance of the armature, resistance of the armature, polar moment of inertia of the rotor, viscous damping coefficient B, right? The torque constant KT and back EMF constant KB, they are given. And then we have to study and plot the speed of the motor, the current in the armature, back EMF, motor torque, for the following cases, right? The first is at t is equal to 10 second input, the voltage input to the motor is 20 volts and there is no disturbance torque. So now we are going to make a Simulink model and model the motor. So what I have done is that for easiness in changing the parameters and then studying the response of the motor for different parameters, I have made program where these parameters are defined, right? And then we will run that program so that these parameters are in the workspace of the MATLAB. And then when we make the Simulink model, we will be able to make model with in terms of the general parameters rather than specific numerical values. And then we will run the Simulink model, and then the model will automatically pick the values of the parameters from the workspace, and then we can see the response of the DC motor. So let us go to the MATLAB. So you can see here I have made a program called DC motor parameters. Let me open that. You can see here DC motor parameters. So I have cleared all the existing variables in the workspace by saying clear all, and then I have defined the inductance, resistance, J, B, KT, KB, and input voltage and the disturbance torque, right? So let us run this. So when we run this, all these parameters will be in the workspace. These parameters will be in the MATLAB workspace. You can see here, this is the workspace, and you will be able to see all these parameters here. Now we would like to make the model in the Simulink. So go to home, and you can see here there is a Simulink icon. Just click this. Now the Simulink will be opened. It will take a few seconds. Oh, it is fast enough. It has opened very quickly. You can see here this Simulink, right? So let us open a blank model. Okay, just click blank model. So now Simulink is open. So this is the GUI of the Simulink, and there is something called library browser which we would like to open first because it contains all the blocks to make the models of the different systems. So you can see here this is the library browser. So this continuous contains the blocks to model the continuous systems, right? Not in discrete systems. The discrete is the models for making the discrete blocks in the discrete systems. So we are concerned with the continuous system models where time is continuous. In the discrete, the time would be discrete. So therefore, in the DC motor, let us first of all make the first part of the electrical part of the motor is the transfer function 1 upon Ls plus A, right? So we have studied the block diagram of the DC motor. So we are essentially going to create that model here in the Simulink. So let us take that block here first. Continuous transfer function. We can take this block, transfer function. You can see here, just click this block, transfer function, and then drag it and drop here. Okay, you can see here it has the transfer function is there. Now this is we can double click this and then define the transfer function what we want to define. So here our transfer function is 1 upon Ls plus A, right? So 1 is the numerator coefficients we have to give here, and then denominator coefficients. So in the denominator we are going to now define it in terms of the general parameters. So our parameters were LA and RA, correct? LA and RA, because they are already there in the workspace. So LA and RA. So then you can see here in this way this defines the transfer function. So if I click this, double click, you can see now the transfer function is numerator coefficients are 1 and denominator coefficients are LA and RA. So this is the transfer function of the, we can even write here, this is the electrical part of the system, right? Electrical part of the motor. Okay, then next after this we have got uh, the mm, the output of the armature circuit. It you know the voltage would be input and the output would be current, and this current then would generate torque. So now we need to define the torque constant. So again we go to the library browser and then define the so the that is defined by the torque constant, the gain of the torque constant, right? Or the gain of the you know this you know uh, current to the torque conversion, which is kT. So let us go to math operation. In the math operation we have what is called as gain. Choose it, drag it and drop it here. Okay, this gain. So this is essentially the torque constant. Okay, and then we can double click this and just call it KT, which is already there in the workspace, right? KT. Then this KT generates torque, and now this torque, the algebraic sum of this motor torque and the disturbance torque, that would essentially determine the net torque on the rotor. So therefore now we need to add also have the disturbance torque and add it to the motor torque. So we will have to have a summation junction here. So in math operation, if you see, you can see here we have this sum, right? So just click it and drag it and drop here. That is summation. Okay, and so we can go into this, and then the different signs we can choose here. So let us take plus and then minus, because plus is for the motor torque, minus is for the disturbance torque. So that is plus minus, right? And now we also need so of course now we can join this. For example, we can just take the cursor to this arrow in front of the block. The shape of the cursor changes to a cross here. Click it and then drag it and connect it to the next block like this. Again, this one I would click and connect it to the summation junction, isn't it? Now the disturbance torque we can define as a some input, right? So let us say it's a unit step disturbance. So we go to the sink here. You can see here in the library browser sink, not sinks, rather source, because it's going to act like a source of the disturbance. So in the here we can go to the source as a step. You can see here step. We click it and we drop it here, drag and drop here, right? So now this we can call as say TL, right? Disturbance torque. And if we go inside this here, now we can provide at what time the disturbance torque enters and what is the initial value, what is the final value, and all that, right? So maybe initially, because we would like to take 0 value, so let us call it 0 here, right? So there is no disturbance torque, but then we need to connect it to the block here like this, so it is connected. So in this way we get now the net torque. Now this net torque acts on the rotor of the motor. So we can just take this part, or maybe we can go back to the continuous list of the continuous functions, and then here we have this transfer function. We can bring it here, right? And we can, this is the mechanical part. Of the motor, right? And then we can double click this, and now we can numerator coefficient is 1, so the transfer function of the mechanical part is 1 upon js plus b. So in the denominator we have j and b, correct? which is already there in the workspace. That is the mechanical part transfer function. Okay. Uh, then we will the output of this mechanical part would be the speed, and then we would like to study how this speed varies. So now we go to the sync, which essentially indicates the blocks where any signal can be fed into, right? So here we can take a scope like this scope, essentially you can call it like an oscilloscope, on which we are going to monitor the speed of the motor, right? Let us place it here and connect the output of the mechanical part to the scope, right? uh, then next we have to uh, this output speed essentially would generate the back EMF, correct? So we are going to now introduce a block for the back EMF. So let us go to the, and again it is defined by the gain KB, right? So it's just a gain. So we go to the math operations. In the math operations we have this gain. We can take this gain and drop it here, and then we would like to change the direction of this. So we just click this, do right click. On the right click you can see here we have this rotate and flip, so we can flip this block, so it changes the direction of the block, right? It's, and then this is nothing but the back EMF, which is back EMF constant, right? So it is essentially KB, and then we double click this and we go here and then we say KB, which is there in the workspace, okay, this KB, and then we connect this to the uh, speed here like this, okay. Now this KB, the output of this block would be back EMF, and this would be then combined with the input voltage being applied to the motor. So now we define a block source. Again we go to sources, and let us say the input voltage is like a step input. So we go to the step here and we get here like this. This is the input voltage. Let us call it input voltage, okay. And now this voltage we can choose as it is given in the problem. Let us go back to the problem. So in the problem it is being said that the voltage is introduced, a step voltage is introduced at t is equal to 10 seconds, and the magnitude of the voltage is 20 volts, right? So let us go to this block, 10 seconds step time. So step time is 10 seconds, initial value is 0 and final value is 20 volts, right? So we say okay, and now we need to add algebraically the input voltage and the back EMF voltage, right? So let us see the browser here. In the browser again we require the summation junction. Go to the math operation and this is here and bring it here, correct? And again we need to make the feedback negative, so plus and then minus, okay. And now we can this we can add here like this. We can connect this input voltage to the summation junction. The output of this can be connected here, that's negative 45, and the error signal has to be given to the electrical part of the motor like this, correct? So you can see in this manner now we have made the block diagram, correct? So now also, as has been asked in the problem, we also need to study what is happening to the current, right? So therefore what we do is that we can just like click this arrow, and in fact you can easily also add any label to this arrow. For example, I can call this current. I'm sorry, this is the torque, by the way, this is the torque, right? So this is the motor torque, motor torque, correct? So and then I can if I click here and then you can add a viewer here. For example, if I click this arrow here, then if I see in the menu there is an option to add viewer. So if I say click this, it's going to ask what kind of viewer you want to add. So let us add a scope here. Okay, so now a viewer has been added here to the motor tool like this. Okay, you can see here. So this symbol here shows that there is a scope added to this arrow. Similarly, this is current. Input to this block is current. So I can just double click this. So I can then add label here current. And if I wish to monitor it, I can just click this arrow, and then in the menu, I can just click this add viewer a scope here. So it's going to add a scope here. You can see here like this. Similarly, if I want to study what is the the torque we have seen, current we have seen, the speed already we have got, correct? So these are the quantities we can study, right? So anything else, if you want to study back EMF, that also you can do. You can, for example, here I can say this is back EMF, right? And then I click this arrow and then add a viewer here. Then I can study back EMF in this. Fine. So you can see now we can perform the simulation, right? So here this we have to choose this top time, that to what time we want to simulate the system. So right now this top time has been taken as 10, right? So maybe let us start with 10 and then just run this. So what it is going to do is Simulink, essentially by making this model. Now the Simulink would be able to internally find a transfer function and a model of this whole combined block, closed loop system, and then it essentially numerically solves this system. For example, if it makes a state space model of this, it will numerically solve that state space model using a numerical method, right, to solve differential equations, and then it gives the output. So let us click this button, run button here, that is, which essentially is for simulating the model. So you can see at the bottom it is showing all the messages like auto save. It's backing up all the unsaved models. Okay, so all the operations it goes through, it basically gives the messages for that. So now it says ready, means so it has given some errors here. Okay, so let us resolve those errors. Load a file into create a new variable. So let us go back to the MATLAB file once here. So yeah, so VITL KB KT. Okay, so let us first of all rerun this file once. So they are there in the workspace, and then also go to this and go to KT. This, let us, I think that K was capital, let us make it capital KT. Okay, KT, and then this KB, that also was capital KB. Okay, so earlier in fact these two gain blocks were shown with red shade, which essentially was a message to us that there is some problem with these blocks, and now you can see it seems that it is resolved. Let us run now the model. Running, its model is running now. Terminate is ready. So the simulation is complete. Okay, so now it has found a solution for all the outputs which we had selected. So let us click the maybe we can also add the input voltage here so that we can see. Let us add a viewer here, and a scope here. Okay, and so that is the input voltage, and we can also That's it. Let us rerun the model so that uh, mm, we are able to maybe also add net torque here. Let us add net torque and also add a viewer to the net torque. Mm, right. Now we can see all signals which are there. Let us rerun the model. That's it. Now the simulation is complete. And now let us look at what is the input voltage we are applying. So if I double click this, now it is showing the input voltage. Okay. Uh, so I think that we did simulation for 10 seconds only, and then the input voltage started acting at 10 seconds. So let us do the simulation for 100 seconds. Let us rerun it. And now look at the input voltage. Now you can see. So this is the voltage we are applying, input voltage to the motor. It becomes non-zero at 10 seconds and then rises to 20 volt instantaneously, right? That is the input voltage. Now this input voltage, let us look at what is the current, how current is changing. So you can see the current suddenly increases initially, right? And then gradually it becomes smaller, smaller, smaller and smaller, and then reaches to a steady state value, right? Let us look at what is the motor torque. Again, you can see the motor torque initially rises to the maximum value and then gradually it decays like this. What is the net torque? Net torque is same as the motor torque because currently the disturbance torque is zero, right? Uh, and then what is happening to the speed? So you can see the speed, it starts gradually rising when the voltage is applied at 10 seconds, right? It gradually rises and then it reaches to a steady state value, correct? And let's look at what is happening to the back EMF. So back EMF also, it starts from zero and gradually it rises and then reaches to some value, right? Steady state value. So, so in this way, you can see we can simulate the motor and study the performance of the motor, right, for different inputs. The next part of the question was that now at t is equal to 100 second, the now TL comes into play. It increases to 2 Newton meter. So now this you can easily incorporate, correct? We can go to the this block. We can double click this thing, and then we can give the time at which the torque comes into play, and then give the final value of the torque, and then simulate the system, and then we can study the response of the steady state motor after this disturbance enters into the system, system. Okay. So this completes the exercise 6, right? Let us go to the next exercise. It's a unity feedback system with plant transfer function given by GS 1 upon S plus 2, and then consider a closed loop system with proportional controller CS Sk with gain K is equal to 1, right? Now simulate the system response to unit step input using Simulink. Study the system response for K is equal to 10 to 100. So this essentially is problem similar to the exercise 5. In exercise 5, we made an explicit MATLAB code to define the transfer function and then make the flow closed loop system, solve the closed loop system for the step response and all that. But in question 7, we are using Simulink essentially to study the performance of a proportional controller. The same problem, we are solving using Simulink, right? So I think this you can easily make. Okay, we already have studied how we can make the block diagram and all that. And then in the next part, in exercise 8, we have to replace the controller in exercise 7 with a PI controller. That is CS is equal to KP plus KI upon S, right? Take KP as 1 and KI as 1 and simulate the system response to unit step input using Simulink. Study the response to a unit ramp input, write your observations. So in both these exercises, what you are supposed to study is that what is the ability of this closed loop control system to ensure that the output of the system tracks the reference input, correct? So that has to be studied. Okay. Uh, so So in the for the controller, you can see here in the library browser, we have the functions like in continuous. If you go, you have like mm, different functions, like you can have this PID controller, for example. In this PID controller, you can choose the proportional gain, integral gain, and derivative gains, right? And study. So of course, for PI controller, derivative gain should be taken as 0, right? And therefore that would be necessary for exercise 8. The other way to model the controller, PI controller, could be that we use two blocks, one for the P as the gain block. For the From the math operations, we can take the gain block here to define the proportional controller gain, and then we can go to the continuous blocks and then use the integrator. Okay, and in the integrator, then we can define the integrator again, and then combine these two blocks, proportional and integral block, using a summation junction. The output of these two blocks can be combined using a summation junction, and then that can be fed to the plant. So that is also a way to model the PI controller. uh, so I think you can solve these problems very easily by the way we have modeled the DC motor. In the same way, you can proceed and solve these problem exercises. Okay. So I think in this way we come to the end of this lab session. Dhanyavad.